Hi, good evening students. Today's topic of discussion is electromagnetic induction. This was discovered by the great physicist Michael Faraday with the help of two activities. So the activity 1 was very famously called as the magnet and coil experiment, and the activity 2 is called as coil and coil experiment. In the previous concept, we studied Oersted's discovery. When a current is passed through a conductor, a magnetic field is produced around the conductor. Now the reverse of this only is electromagnetic induction, what we are going to discuss today. So in the earlier experiment of Oersted, we said that a current passing through a conductor can produce a magnetic field. Like that, variations in the magnetic field can produce current. The reverse effect of Oersted's discovery only we are going to discuss today with the help of two activities. Okay, now you look at the activity 1. It is called the magnet and coil experiment because for this activity a bar magnet and a solenoidal coil are being used. Now this is a solenoid. The two ends of the solenoid are connected to an instrument represented by capital G. This instrument is called moving coil galvanometer. So the expanded diagram is shown here. This instrument is called moving coil galvanometer. Okay. So what for it is used means it is used to detect current, in a circuit. Already we have studied the instruments, namely ampere meter or ammeter. That instrument ammeter is used to measure the current, but this instrument moving coil galvanometer is used only to detect the presence of current. Okay. If current is passing through the circuit means the instrument will be getting deflected either left side or right side. Now you can see the moving coil galvanometer is having a pointer. This pointer is reading 0 when it is not connected to the circuit. So I have shown here the galvanometer is pointing towards what? 0. Because at present there is no current flowing through the circuit. Whenever a current is flowing through the circuit means the pointer cannot rest in 0. Either towards the right or towards the left depending upon the direction of flow of current. Such an instrument which is used only to detect the presence of current in a circuit is called as a moving coil galvanometer. Okay students, now you look at the circuit once again. There is a solenoidal coil. The two ends of the solenoidal coil are connected to a moving coil galvanometer. And to the left side of the coil you can see a bar magnet, and this bar magnet is at rest now. It is at rest. So will there be a magnetic field surrounding the bar magnet or not? We have already given the introduction about the magnetic lines of force. Magnetic lines of force start from which pole? From the north pole, and end in which pole? In the south pole. And this magnetic field is always present in the region surrounding the bar magnet. So I will show you some of the lines of force like this. Okay. So from the north to the south, okay, these are the magnetic lines of force. Like that, now you can see here there are a few magnetic lines of force coming out of the north pole. Are they in contact with the coil now? Can you see that the magnetic lines of force starting from the north pole, they are going to end in the south pole in this space surrounding the magnet. But can you see a few number of lines like this? See, these lines are all in touch with the coil. Yes. So I can say that the magnetic field lines are in contact with the coil. Okay, when the magnet is not at all moving, when the magnet is at rest, you will see that only a few number of lines of force will be in contact with the coil. Now what is going to happen when the magnet is pushed towards the coil? The magnet is going to move. So I have shown here the magnet is moving in which direction I have shown? From the left to the right. So when the magnet is pushed inside means at each and every second, what is going to happen? More and more number of lines, more and more magnetic lines of force will come in contact with the coil. Isn't that? So I have already told you that the magnetic lines are also called by the name magnetic flux. Magnetic lines of force are also called as what? Magnetic flux lines. Okay, so these lines are also called as what? Magnetic flux lines. So when the magnet is now deeply moved inside the coil, almost the entire magnetic field of the bar magnet will be in contact with the solenoid. Then again it is pushed out on the other end. When the magnet is coming through the other end, suppose you see that when the magnet, so it has entered from the left hand side of the solenoid and it has come out, now come out on the right side of the solenoid. So when it is moving from the left end to the right end, what should have happened? I will tell you. So initially when the magnet was coming towards the coil, less number of magnetic flux, less number of magnetic lines of force only will be in contact with the coil. When the magnet is deeply penetrating inside the coil, means almost the entire magnetic field surrounding the bar magnet should be in contact with the coil. And when the magnet is coming out slowly, again what happens? The magnetic flux lines or the magnetic field lines in contact with the coil will diminish. Again I am going to repeat in the reverse direction. So in the forward direction, which pole entered the solenoid? You see the north pole. And now I am going to reverse it. So when the magnet is moved in the reverse now, which pole is entering first? It is the south pole. Is it not? Before that, once again I will tell you. Initially which pole was entering? The north pole. So when the north pole was entering, initially very few number of magnetic field lines only were in contact with the coil. And then as the magnet is pushed inside the coil, each and every instant of time, the magnetic field lines or the number of magnetic flux lines linked with the coil is continuously increasing or it is changing continuously. As a result, now what happened? What was observed by Michael Faraday during the movement of the magnet? The galvanometer was deflected. The galvanometer was deflected in a particular direction. And when the magnet was totally brought to the other end and stopped, at that moment what happened? The galvanometer was deflecting 0 because the magnet has stopped. When the magnet has stopped on the other end, what will happen? The same number of flux lines only will be linked with the coil and there is no change in the magnetic field lines. Is it not? Again, he tried to do the experiment in the opposite direction so that you see that now the south pole is going to enter inside. So when the magnet was pushed inside, again there was a deflection in the galvanometer, but this time the deflection was in a direction opposite to that of the first step. Okay. In the first step, if the deflection was on the right side, means now when during the reverse direction, the deflection was also reversed. Again and again, when the magnet was moved in a particular direction, deflection was also in the same direction. When the magnet was pushed in the reverse direction, deflection also was reversed. And again, it was repeated again and again. And it was confirmed that this deflection in the galvanometer is because of some current flowing in the circuit. Okay, and this current will be observed in the circuit so long as there is a change in the magnetic field lines linked with the circuit. Suppose if the entire magnet is placed at the center of the coil at rest permanently, okay, no movement of the magnet was observed, but the total magnetic field is associated with the coil itself. But now there was no deflection. Why? Because when the magnet is at rest, there can be no change in the flux. There can be no change in the magnetic field lines linking the circuit. So Michael Faraday confirmed that there is a deflection in the galvanometer whenever there is a movement of the magnet. Understand? Okay. Whenever the magnet moves, what is actually happening? What is the relationship between the movement of the magnet and the current here? When the magnet moves, then only the number of magnetic field lines linking the circuit will change. Understand? This change in the magnetic field lines only is very important for us, not the total number of lines. by how much there is a change in the magnetic field lines only is very important for us. Have you understood? So I will tell you. So whenever the magnet is moved inside a fixed coil, there was a deflection in the galvanometer. So there is a change in the magnetic field lines. As a result of the change in the magnetic field lines, an EMF is induced. Okay, an EMF or potential difference. Okay, potential difference is induced. And whenever there is an EMF in the circuit, a current will flow because it is a closed circuit. It is a closed circuit. And hence, this EMF is induced. As a result, a current is induced. Okay, a current also is induced in the circuit. Okay, this word is very important. Induced. The current is called as induced current and the EMF is called as induced EMF. Because this EMF will stay in the circuit so long as the magnet is in movement. Okay, so this is one of the activities. And finally, some other modifications were also done by Michael Faraday. So initially he kept the coil fixed and the magnet only was moved in and out. Okay, and there was a continuous deflection, okay, in two opposite directions. Then he fixed the magnet. He fixed the magnet and then he moved the coil over the magnet in two opposite directions. In this case also, there was a deflection in the circuit, there was an induced EMF and an induced current was flowing in the circuit. Third time, he moved both the coil as well as the magnet at a time in opposite directions like this. When he moved, both were in movement. In this case also, there was an EMF induced in the circuit and the galvanometer was showing induced current in the circuit. Finally, he confirmed that there should be a relative motion between the coil and the magnet. So this is very important, relative motion. Okay, so in this case there should be relative motion between the magnet and the coil. Okay, so whenever there is a change in the magnetic flux or whenever there is a change in the magnetic field lines linked with the circuit, an EMF is induced and a current is also induced. This induced current flows only in the closed circuit. So this phenomenon of inducing an EMF and hence a current in a closed circuit. Okay, how? Whenever there is a change in the magnetic field lines, this phenomenon only is called as electromagnetic induction. Okay, now you look at the activity number 2. What is the name of this experiment? Is coil and coil experiment. So two coils are placed coaxially. Okay, one is placed side to the other. So coaxial coils. And you see that the first coil is called by the name primary coil and this primary coil is connected to a battery and a key in series, plug key. And the second coil is called by the name secondary coil. And this coil is connected to a moving coil galvanometer as before. So it is a center zero galvanometer. Okay. Now here I will just plug in the key now. Okay. So when I plug in the key, what is going to happen? The moment I plug in the key, current will start to flow, that's all. It will not attain the maximum value. For example, when the key is opened, what should be the current flowing in the circuit now when the key is opened? 0. Okay, so I will take here now. Now the current is equal to what? I equal to 0 because the key is opened. And let us say that when the key is closed, the conventional current starts from which terminal? The positive terminal, and it ends its journey in the negative terminal. Let the maximum current supplied by this battery is 1 ampere. Understand? So what is going to happen when you close the key? At that moment, the current will change from 0 ampere to some higher value. Understand? So due to this change in current, here a magnetic field will be induced. Okay, a magnetic field will be produced in the axis of the solenoid. We have already studied, no, when current flows through a solenoid means a magnetic field will be produced at its center. Understand? And the magnetic field will be uniform magnetic field. Can you see here some magnetic lines? Some magnetic lines are produced by the primary coil, but this magnetic field of the first coil is also linked with the secondary coil. Okay, like this. Some other lines also you can take like this. So some of the magnetic field lines of the primary coil will also be linked with the secondary coil because both are in close proximity. They are in the vicinity of each other, close to each other. Okay. So the magnetic flux produced, the magnetic field produced by the primary coil will also be in contact with that of the secondary coil. Okay. But when the current has reached its maximum value of 1 ampere. Okay. When the current has reached its maximum, that there is no more change in the current means this magnetic field is not going to change. So what I want to say is, when there was no current, that is when the current in the circuit was 0, there was no magnetic field inside the primary coil. But when I close the key, immediately what happens? Current starts to flow. It will not attain the maximum value immediately. Okay. So though the maximum current is 1 ampere, in between 0.2 ampere, 0.4 ampere, 0.6 ampere, like that the current should have increased. This increase or change in current will take place in a definite time. So whenever the current increases from 0 to a maximum, though the time is very short, during that short period of time, the current is changing from 0 to a maximum. During that change in current, the magnetic field associated with the primary coil also will change. Understand? So this is called from 0 to maximum. This is called as what? Growth of current. Growth of current. So this change in current is called as what? Growth of current. So when the key was opened, the current was 0. When the key was closed, immediately the current will not attain 1 ampere. So it will take at least 1 by 10 power 6 second or 1 by 10 power 9 second or microsecond to nanosecond, you can say. In that time the current is changing or not? Okay, whenever the current changes, the magnetic field of the solenoid will also change. That is why during this change in the magnetic field, the magnetic field changes taking place in the primary coil will also take place in the secondary coil. As a result, the galvanometer will be deflected. Understand? The galvanometer in the secondary coil will be deflected only during the change in the current or change in the magnetic field occurring in the primary coil. Once the current has reached its maximum, even when the key is closed, when the current has reached its maximum value and there is no more further increase in the current or change in the current, the galvanometer will come back to 0. So this will happen. Once again I am going to remove the plug key now. You see here I am removing the plug key. What will happen now? The current will now come down from 1 ampere to 0 ampere in the reverse. You see here now it is coming from 1 ampere to 0 ampere, but in steps. That is 1 ampere, 0.6 ampere, 0.4, 0.2 ampere, then only 0 ampere. So it will take some definite time, but it is a very less time. In that less time also, does the current now change or not from a maximum to 0? During this instant of time. During this time, when the current changes, the magnetic field lines or the magnetic flux lines linked with the primary as well as the secondary also will change. Now also there will be deflection in the galvanometer. Once again, when the current has come to 0 totally, the deflection will come back to 0. Are you all understanding? Look here, very quickly I am explaining once again. Just when the key was initially opened, the galvanometer was not showing any deflection. The moment I will plug in the key, quickly the deflection will be there and again it will come back to 0. Why? Because the current has already reached its maximum value. So why the deflection was there? Because the current was changing from 0 ampere to 1 ampere within a short period of time. So this is called as a make of the circuit. Okay, make of the circuit. Make of the circuit. During the make of the circuit, current increases from 0 to maximum. So I will write current increases. Okay, during the make of the circuit. Okay, during the make of the circuit. Okay, this is the first point. Current increases from 0 to maximum. Okay, so during the make of the circuit, current increases from 0 to maximum. So current changes. As a result, what happens to the magnetic field linked with the primary coil? It also changes. As a result, the magnetic field linked with the secondary coil also will change. So during that change, the deflection will be momentary. The deflection will be momentary. Okay. Now, second point. During the break of the circuit. During the break of the circuit. Means what? I remove the plug key now. I open it. So during the break of the circuit, the current decreases. Okay, the current decreases from maximum. Okay, decreases from maximum to 0. Okay, this are you understanding or not? It is a reverse of the previous step. So during the first make of the circuit, I just close the key. Now current increases from 0 to maximum. In this time, the current changes. The magnetic field linked with the primary coil as well as the secondary coil also changes. So there is a mutual understanding between the first coil and the second coil. It is also called as mutual induction. In higher studies, you are going to study. It is called mutual induction. Understand? Anyhow, students, now you see that here in the second experiment, that is activity number 2, which is called as a coil and coil experiment. How many coils we are using is 2 coils. The first coil, which is connected to the battery and key, is called as the primary coil. In the primary coil, whenever we close the circuit, the current in the primary coil changes from 0 to maximum, during which the magnetic field in the primary coil is going to change. Understand? See, already I have told you that the magnetic field due to the solenoid, is given by what? Mu naught into N into I. That is, B is proportional to I. Is it not? I told you the magnetic field strength is directly proportional to the current flowing through the solenoid. So when the current is 0, the magnetic field will be 0. When the current is maximum, the magnetic field will be maximum. In between 0 and maximum, when the current passes through the values 0.4, 0.6, like that, during which the current changes, the magnetic field also will change. So during the change of the magnetic field only, there will be deflection in the galvanometer in the secondary coil. Okay. So once again, during the make of the circuit, the current increases from 0 to a maximum. So when the current increases from 0 to maximum, magnetic field also will be increasing from 0 to maximum. During this change in the magnetic field linked with the secondary coil, an EMF will be induced and a current will be induced. Similarly, during the break of the circuit, that is when I remove the plug key, current will not become 0 immediately. It has to come down from 1 ampere to 0 ampere through 0.8, 0.6, 0.4, 0.2, 0.1, like that. During this change, though this change will take place very quickly, but in that short time, what is happening? The current in the primary coil decreases, so the magnetic field linked with the primary coil decreases. As a consequence, the magnetic field linked with the secondary coil also will decrease. So during the make and break of the circuit, okay, this is very important point. During the make and break, okay, during the make and break of the circuit, okay, the EMF will be induced. So now you see, you imagine, first I will keep the plug key closed. Quickly I will take out. I will keep, again I will take out. I will plug in, I will plug out. Like that, you imagine whenever I plug in, that's deflection, and whenever I plug out, I will see another deflection. During the plug in, left side deflection, and during the plug out, okay, right side deflection. Like this, alternately during the make and break of the circuit, there will be deflection. Once you plug in and half an hour, if you are watching the switch, means half an hour the plug is closed, and whenever you see the galvanometer, will it show deflection continuously? Means no. Why? Because the current, constant current, when it is flowing through the circuit, means the magnetic field also will be constant, so that there is no change in the magnetic field. Is it not? So though the current is flowing through the circuit, if constant current will flow, means there is no deflection, because the magnetic field strength does not change. Because electromagnetic induction itself is what related to the change in the magnetic field or change in the magnetic flux. So my dear students, now I am going to summarize from the activity number 1 and activity number 2. We find that there is a current induced in the circuit whenever there is a change in the magnetic flux, or whenever there is a change in the magnetic field lines linked with the coil or circuit. This phenomenon only is called as electromagnetic induction, and this was discovered by Michael Faraday. So what is the statement of electromagnetic induction, shall we see? Electromagnetic induction is defined as the phenomenon of inducing an EMF and hence a current in a closed circuit whenever the magnetic field lines linked with the circuit or coil changes. Understand? Suppose if you move the magnet very fast, means deflection also will be very fast. Why? This is directly proportional to the speed of movement of the magnet. Understand? Like that, here also, if the key is very frequently, okay, plugged in and plugged out. Okay, when you do it slowly, the current also will be what? The EMF and the current also will be what? Very less. And very fast if you do, means more EMF also can be induced. And take care that this EMF must be called by the name induced EMF only, and the current must be called as what? Induced current only. Understand? Okay. So once again I will tell you, my dear students, electromagnetic induction is the phenomenon of inducing an EMF and current in a closed circuit by changing the magnetic field lines linked with the circuit or coil. Have you all understood? Okay, fine. We will see in the next topic. In electromagnetic induction, instead of moving the magnet, we can fix the magnet and move the coil. Okay? So there is a relationship between the direction of motion of the coil, direction of the magnetic field, and the direction of the induced current. This relationship only is given by Fleming's right hand rule, and it is getting another name also, which is called as generator rule. Okay. So what is the statement? For that, we will stretch the right hand such that the thumb, the forefinger and the middle finger are perpendicular to each other mutually. Okay? If the thumb indicates the direction of motion of the coil or conductor, and the forefinger indicates the direction of the magnetic field, then this middle finger indicates the direction of the induced current. Understand? So now we can look at this picture. These three fingers, namely forefinger, middle finger and the thumb, okay, they are stretched perpendicular to each other. You see here, I am stretching like this I have kept. So this is forefinger is shown at the top, and the middle finger is shown towards the left. Now is the thumb pointing towards you in this position. Okay. Now what are the quantities represented by the three fingers? The thumb indicates what? Motion of a conductor. Thumb indicates motion of a conductor, and the forefinger indicates what? Direction of the magnetic field. Okay, direction of the magnetic field. And the middle finger indicates the direction of what? Induced current. Okay, induced current. And this rule also is called as a generator rule, because it is the principle of working of the dynamo or a AC generator. That is the next topic what we are going to see. Understand? I hope you must have understood. Okay, the next topic is AC generator. Okay, fine.